University. This is going to be a very, very elementary lecture. In fact, I am fascinated by path integrals. I encountered path integrals when I was a postdoc abroad in England. I went for a summer school in Cambridge University, and there was a speaker who spoke about path integrals, and that was the first time. So therefore, I encountered path integrals rather late in my research career. But since then, it has become one of my fascinations. Actually, there was a time when I was really mad about path integrals. Whatever I was thinking, I was always thinking of path integrals actually. But of course, that period is gone now. But still, I use it in my research. In fact, I find this as a very convenient tool to think. Quantum mechanics, as you know, is not an easy subject to understand. But to me, when I encountered path integrals, I thought I have understood quantum mechanics in whatever fashion it can be understood, because path integrals actually make it very simple and very elegant. So therefore, my own feeling is that this should be taught to the master's students. But of course, path integrals has the difficulty. The difficulty is that it is nice to think about path integrals, but actual evaluation of path integrals is extremely difficult. So you know that in the evaluating one integral itself can be messy. It is very difficult. But path integrals, I will write an expression for the path integrals, I think, perhaps. It involves an infinite number of integrals. All these integrals have to be done. And you know that evaluating even a single integral is difficult. And so how can you evaluate an infinite number of integrals, all of which occur in the same expression? That is rather difficult, but in some cases, actually, we can do it. And of course, there are approximation procedures for evaluating path integrals. In fact, you see, the normal way of doing quantum mechanics is you write down the Schrodinger equation and solve it. But what path integrals does is actually it straight away writes the solution, but the solution is written as an infinite integral. That means integration over an infinite number of variables. So you straight away have the answer, and the problem is how do you evaluate these integrals? As I said, it can be done only in certain cases, certain special cases. But then if people have devised approximation procedures and they have used it even to numerically evaluate path integrals and so on. It is a vast area and in fact, very interesting, very nice area. So with that very quick introduction, let me start the talk by wishing you all a very good evening. This I probably should have wished it right in the beginning before I spoke. Anyway, so the title actually, I didn't say path integral formulation in quantum mechanics because my talk is going to be a little bit more general. Path integrals is of great utility in Brownian motion. It is of great utility in, as you know, field theory and so on. So, I mean, it is useful in many different areas. In fact, there is a nice book by Kleinert. If you look into that book, you will find different areas in which this is applied. Path integrals are applied. Even financial markets have been dealt with using path integrals. So it is a vast area, and I would like to remember my friend Professor Sabir. And my only hope is that if he was around, he probably would have liked my talk. And this, of course, is my name and my affiliation as of now. But this affiliation is valid only till the end of November. In the end of November, in the beginning of December, I actually shall move to Cochin and I will live in my house in Cochin, very near the university. So here's an outline of what I'm going to speak. I will remind you of diffusion of a colloidal particle. And in fact, diffusion of a colloidal particle, there is a very nice approach which is almost the same as the path integral approach. You think of a random walker and you have some object which is referred to as the functional integral. Functional integrals are very well-defined objects mathematically, whereas path integrals themselves, as they occur in quantum mechanics, their mathematical theory is not very well developed. But these are integrals similar to the path integrals in quantum mechanics with well-defined mathematics. This was originally introduced by Wiener in 1918. Wiener was working on Brownian motion, and in fact, he introduced these integrals in mathematics. But of course, this was unknown in the physics literature until Feynman introduced his famous path integral around the year 1941, 42, 43. I don't remember the year. So after talking about these so-called functional integrals, I shall speak about the two-slit experiment. And from that, actually, Feynman conceived the idea of the path integral. I shall tell you about that. One of the very nice things is that you see, if you formulate or if you make use of the path integral formulation of quantum mechanics, actually, it is fairly easy to argue that classical mechanics should follow in the limit where the value of h cross, the Planck's constant, divided by 2 pi, approaches zero. You know that you see if h cross is zero, then of course the whole thing has to reduce to quantum mechanics has to reduce to classical mechanics. And in fact, if you are prepared to do some hand-waving arguments, then you can show that classical mechanics follows. The principle of least action follows very easily from the path integral formalism. And I shall also give you some ideas about integration over function spaces. Path integrals as well as functional integrals are special cases of the ideas of integration over function spaces. This is an idea that the MSc students are not likely to be familiar. And then, of course, I will also tell you how to evaluate a path integral. And I hope I can cover all this. I think I don't have that many slides, and therefore I should be able to cover. Perhaps I may even not fill up the time that is available to me. Okay, because you see, this is the first time ever that I'm giving this talk. So let me start with Brownian motion. Now, what is Brownian motion? Well, as you know, as all the students know, this was observed in the case of colloidal particles. So imagine, I hope you can see my mouse, right? So these are colloidal particles. In fact, colloidal gold, let us say, these are particles that you can see if you use a microscope, essentially because they scatter light and therefore you can see tiny dots when you observe colloidal gold under a microscope. And imagine you have put colloidal gold in water. Imagine they are concentrated in this region. Then, as you know, what will happen is that as time passes, these particles will diffuse. And what will happen? They will spread throughout the solution. This, as you know, is only a natural thing. That is the process of diffusion. Now, how does the diffusion process take place is the question. The answer is that you see the molecules of water which are surrounding these particles, they are actually moving completely randomly in all possible directions. So what will happen is that they will come and hit these colloidal particles randomly. And at any particular instant, you see there will be molecules, let us say, hitting this particular colloid. And the number of hits from one side may be different, would be definitely different from the number of hits from the other side. So therefore, the momentum transferred to the particle, the colloidal particle will vary as time passes. And because the momentum transferred varies, what will happen is that the particle will start moving. So let us say it starts moving in this direction, it will maybe go up to there. Then suddenly there are many particles hitting from the other side. So then the colloidal particle will start moving in a different direction. In fact, I have an animation in the next slide, which is taken from the web. I claim no credit for the animation. So this is the animation. This is supposed to be your colloidal particle, and these red small spheres represent your water molecules. Let us say water molecules, of course, are not spheres. So this, you just say that it is an animation of Brownian of a colloidal particle in a solvent. So this is the so you can see that the colloidal particle actually is moving in random directions. You see, it is not moving in a definite direction. So it moves in one direction a little bit, and then suddenly its direction of motion changes. Why does it happen? Because the collisions from the water molecules are random, and therefore the momentum transferred varies from instant to instant, that is pushing the colloidal particle in different directions. So this is the kind of motion that I would like to think of first of all. And from this kind of motion, we will arrive at the idea of a functional integral. So if you wanted to model the motion of such a particle, how will you model the motion? The answer is actually mathematicians have nice way of modeling things. And the mathematicians, well, you see, they would say that, okay, the motion of this colloidal particle, in fact, this is what Einstein did long ago in 1905, I believe. He said that this is actually similar to the motion of a drunken walker. In fact, my previous lecture, which I had given, I don't know how many of you have listened to it, introduced the Captain Haddock, who is a drunken person who likes to drink. And what he does is he goes to the bar every evening and gets drunk. He will be in the bar for some time and then he comes out and starts walking. And this walk is what is typically referred to as a random walk or a drunken person's walk. And the nice thing is that, or the interesting thing is that he is so drunk that he has absolutely no sense of direction. And therefore, a mathematician would say that, okay, each step that he takes is in a direction that is independent of the direction of the previous step. So if he takes a step in the northern direction, the next step that he takes will never be in the northern, well, it may be in the north direction, or it may be in the west direction, or in the south, or in the east, or in any direction. So if you think of the angle between the two directions, they can be anywhere between 0 and 360. So that is the kind of walk. And so if you observe him, suppose you observe him, you see on one day, then he would have followed this path, and at the end of 1 hour, he would be arriving found at this location. Because you see, even though he wants to go home, he has no sense of direction, and therefore he executes a random walk. And after walking for 1 hour, he ends up here. And if you observed him on subsequent days, what will happen is that he will be seen to be taking different paths like this or like that, or any of these different possible paths. So this is what happens. And therefore, the question is, what kind of predictions can we make? As a scientist, I am interested in making, let us say, experimentally verifiable predictions. And what kind of predictions can I make? If we have such a work, well, this has been analyzed by mathematicians at first, and of course, by physicists too. So actually, I mean, if you make it sound a little bit more mathematical, this is essentially a random walk in 2 dimensions. Why? Because he is walking on a plane on the earth. So this is a random walk in 2 dimensions, whereas in the case of the colloidal particle, remember the colloidal particle was moving in 3-dimensional space inside a solution. So that will be referred to as a random walk in 3 dimensions. You can also say that, okay, I will confine my walker to move along a line. So we can take steps only in the forward or in the backward directions. He cannot go out of the line. So that will be random walk in 1 dimension. And that is, of course, is the simplest. So imagine now, see, the studying him, and then on one day, you know that he is going to come out of the bar and start walking. And suppose you ask, where will he be after 1 hour? And of course, this is something that you cannot say with any certainty. But then, of course, mathematicians have analyzed this kind of problem, and what they will do is they can do is they can actually talk about probability of finding him. For example, what is the probability of finding him? Let us say 10 kilometers away from the bar, and obviously the answer is would be zero or almost zero. But then what will happen is that if he starts here and after 1 hour, you see, it is likely that you will be within maybe 100 or 200 meters of this bar. And as you approach the point of starting the walk, so that means as you approach here, the probability of finding him, it is likely to increase. So therefore, you would expect that as the near the starting point, the probability of finding him will be large, and as you go away from the starting point, the probability of finding him will go on decreasing. So that is the kind of thing that one can, even without doing mathematics, say. So therefore, what I am saying is that you see, he could have taken actually this possible path on a particular day, which means that he would have ended up here, and then I would say that, okay, this means that he has displacement from the initial position, which I denote as x. This is the displacement from the initial position. And let me say after a time t, I shall be introducing t later. So therefore, let us say after a time t, the probability density of finding him at this location can be calculated, and will be written as p of x comma t. Probability density, remember why probability density? Because if you took a small area around this point, let us say the area is actually denoted by dx, okay, d vector of x, then what you have to do is you take this probability density multiplied by dx, and then you will get the probability. That is why we say probability density. And this probability density, okay, here is x and t, so therefore the question is this: he has actually started here at 0 time, and I want to calculate the probability density of finding him at this location at x. So this vectorial distance from the starting point to the final position is x. And I want to calculate the probability density of finding him there at after a time t. So therefore, that is what I would like to calculate. And you can think about this actually. If you think about it, you see, in order to reach this point after a time t, that means the point x at the time t, given that he has started at the origin, I will take this to be the origin, and his starting time has to be 0. So therefore, he starts at the origin at 0 time, and I want to calculate the probability density of finding him at x after a time t. So how do I calculate this probability? You think about it. I'm not going to write down an equation. Well, I may have an equation, but don't worry, I'm not going to derive it. I will really make it plausible. So in order to do that, you see, he could have, for example, taken this path. What is the property of this path? I hope you can see this path, the black path. The property is that this path will start at this point, at the origin, at the time 0. He walks along, and the path, of course, has to end at x after the time t. So that is one possible path. You could have taken that path on a particular day. Or see, if you wanted to calculate the probability density of finding him there, then you could have taken this path. That also is a possible path that you could have taken. It also has the same kind of properties. That means that it starts here at 0 time and ends there after a time t. Or he could have taken this path again. Well, all of them start at 0, 0. That means at 0 position, at 0 time, end so they have drawn only 4 paths, but then if you think about it, you would realize that you can think of an infinite number of such paths. See, for example, I will only show the such a path with the mouse. So you could have gone, sorry, you could have gone like that. You could have gone like that. Maybe you would have gone something like that, and then eventually Coming back here, of course, you have to satisfy the condition that the random walker has to be back here at x after the time t. So all the paths that I consider have that property. So any such path in principle he could have taken. But of course, then when you think about it, you would also realize that some paths you would expect are more likely than others, right? See, for example, so a path like that, you would have expected that somehow it would be less probable, right? Or as I usually say, well, you see, today I'm in Bangalore, so therefore he starts here in principle. He starts at the bar, and then let us say he goes to IISc, which is about 6 kilometers away, and comes back. Even such a path, in at least in principle, he can take, but in practical purposes, that is just impossible. So therefore, you would say that the probability of such a path is very, very, very small. Whereas the paths that are shown here in the figure are actually much more probable than a path which goes very far away and comes back. So therefore, you realize that when you have a path, actually, it is possible to assign something like a probability for each path, right? So therefore, I can assign a probability for this path, another one for that path, another one for that path. So therefore, you would also realize that the probability that assigned to this path will depend upon how convoluted this path is. For example, this path perhaps is more probable than a path which goes to IISc. So therefore, the 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 probability that assign depends upon the whole path. Or as one would say, as a mathematician would say, it is a functional. The probability is a functional of the path. You give me a path, I will be able to assign. You give me a path, I will be able to assign a number, a probability a functional. A path, as you know, is a function, but when I say functional, you say to each function you are assigning a number. Fine. So that introduces very quickly the idea of a functional. In fact, this is an expression that you need not worry about this at this point of time. Hopefully, I shall describe this in more detail if time permits. Okay. So the idea is that you see you have the probability density. I told you probability density of finding the person at x at the time t. That is p. P is a function of x and t because x is the final position and t is the final time. So what should you do? For each path, you are assigning a probability, and in the case of Brownian motion or the random walker, what happens is that this exponential term, you look at this exponential term, there is a e to the power of minus 1 by 4d. D is just a constant, and it is known as the diffusion coefficient of the random walker. So therefore, you have minus 1 by 4d. D is just a constant. You see, I mean, it depends upon how fast the person is walking and so on. And then you have the functional that I talked about. You see, you take the path, a particular path, which you denote as x of s. X of s actually describes the whole path. S is time. So as s changes, you see the position of the random walker is changing. So therefore, what you have to do is you have to take the derivative of the position of the random walker with the time. That means you are actually getting velocity here, right? So and therefore this is actually velocity the whole square. It is very much analogous to kinetic energy because kinetic energy contains we have mass into velocity square, whereas here you don't have mass, you have this 1 by 4d. And then of course you have to integrate from the beginning of the path to the end of the path. This is actually an idea thought about by Feynman. He said that, okay, you know what happens in the case of two-slit experiment. In the two-slit experiment, what is happening is that the wave associated with the electron, with the single electron, it passes through both the slits. So imagine you had a more complex arrangement where you have three walls. Each one of them has two slits, right? Then what can happen is that the wave associated with the electron can pass through both of the slits in the first wall, both of the slits in the second wall, and both of the slits in the third wall. So therefore, if you think of the possible paths that the waves could follow, then you see there are actually 8 different possible paths. For example, this green path is one possible path that the wave could have taken. So it starts, the electron starts here, it goes there, through this slit, then through this slit, then goes there, and then eventually arrives at this location. But that is only one possible path that the electron could have taken. This red one is another one, and this with this light or green or this blue one is another one. I have drawn only 3 so that the picture is clear. But because there are 3 walls and each one has 2 slits, obviously there are 2 to the power of 3. That is actually 8 different possibilities. So therefore, you have to say that, okay, there are the 8 different possible ways for the electron to travel from here and arrive there at the detector. And what will happen? Each such possible way will make a contribution to the wave or to the, strictly speaking, to the wave function. So therefore, what I should do is, I should have some formula to calculate the contribution. And once I calculated the contribution of all these 8 possible paths, what I should do is I should add them up. And depending upon the sum, you see, if the sum is large, then there will be a large probability of finding the electron at this location. While if the sum is 0, there will be no probability of finding the electron. In fact, if you wanted to calculate the probability, what you have to do is first calculate the wave function by summing together all these contributions and then take the magnitude and square it. That will give you the probability density. So that again should be simple and clear. And then Feynman said, okay, let us think of more complex arrangement where you would have, well, in this case, I think there are 12 walls. On each one of the walls, imagine there are 4 slits. So therefore, in total, you see, there are 4 to the power of 12 different possible ways in which the electron could go. 4 to the power of 12 paths that the electron could take, starting here at the initial time and ending there at the final time. And all these paths will make a contribution to the wave function. You have to calculate the contribution of each one of them, right? And then sum over all the contributions from all the possible paths. And that will give me the wave function. And once you get the wave function, take its magnitude and square it. You will get the probability density of finding the electron at this location. So therefore, if you agree with that, then he said, okay, let us make it more complex. And now he has doubled the number of slits on each wall. So if it was 4 to the power of 12 initially, what now happens is that you have 8 to the power of 12 possible paths. Now you can go on imagining this because you see, Feynman, of course, was a theoretician, and theoreticians can just imagine doing things, which is nice because they don't really have to do it. It happens only in their mind. So what he imagined is, you see, you can imagine that you have an infinite number of walls between your source and the detector. On each wall, you go on making more and more slits. And then what will happen? The number of contributing paths actually goes on increasing. So eventually, suppose you have made so many slits on each wall so that each wall is there, but the number of slits that you have made is so large that the walls have become completely transparent, which means that the slits have filled up the walls. So therefore, I can say that, okay, the walls are there in my mind and the slits are also there in my mind. In fact, what I am saying is that the electron is propagating in free space, and when the electron is propagating in free space, what is the conclusion? The conclusion is that you think of all possible paths starting there and ending there after, let us say, 100 nanoseconds. So there would be an infinite number of such possible paths. The only condition that you put on these paths is that they all have to start here at the time 0 and end there at this location after 100 nanoseconds. Obviously, there are an infinite number of such paths. And each path will make a contribution to the wave function. This is the idea of Feynman, and therefore you have to calculate the contribution of any particular path and then sum over all the possible paths. This is very much like the motion of your random walker. Imagine I wanted to calculate the probability density of finding the random walker at a particular location after a given time. Then I thought of all possible paths, starting at the initial location, ending there after a finite amount of time. Then all these paths make a contribution. It is exactly the same kind of idea, but it is also different in the sense that here you see you are calculating the wave function. So therefore, what happens is that you see essentially in the limit where I have an infinite number of walls, each with infinite number of slits, essentially what we are talking about is the propagation of the electron in free space. So how does the electron propagate in free space? Well, if you are here and if you want to calculate the probability, if the electron is initially here at the time 0, and if you want to calculate the probability of finding the electron at this location after 100 nanoseconds, the answer is that you have to think of all possible paths starting here now and ending there after 100 nanoseconds. All such paths. This blue path, this red path, and this green path are only 3 of them, but you think of all the possible paths. Each path will make a contribution to the wave function. And so you calculate that contribution, sum over all the possible paths, you will get the total wave function. And once you get the total wave function, what do? You take its magnitude and square it, you will get the probability density of finding the electron at this location. So this was was introduced by Feynman, the formalism introduced by Feynman. So therefore, if you wanted to calculate the wave function for the electron psi, what you have to do is you have to calculate the contribution of any possible paths. You see, for example, if you have this green path, you have to calculate its contribution. In fact, Feynman wrote down a nice formula for the contribution of a particular path. What is the contribution of a particular path? You see, if it followed this path, you see, at any instant of time, the part electron would have a position because it is following this particular path. So when I say a particular path, that what I am saying is that a particular path is one which specifies its position as a function of time. So if you know position as a function of time, the path is fully specified. And the conditions I have already told you repeatedly. Let me repeat once more. The paths have to start here now and end there after 100 nanoseconds. So this path means you have the position of the particle electron known as a function of time. And once you know the position of the electron as a function of time, you can calculate the action associated with that path. In classical mechanics, you see, if you know a particular path, that means if you know x as a function of time, then you can calculate the action that is associated with the path. And that is precisely the thing that occurs in quantum mechanics. So you, for a particular path, you calculate the action multiplied by I is square root of -1, and then of course we are going to have quantum mechanics, so it is only natural that the Planck's constant occurs in the expression. So therefore you have h cross, the whole thing divided by h cross. Then you take the exponential. Once you take the exponential of such an object, this object is purely imaginary. But when you take the exponential, you will get a complex number with the real part and imaginary part, and the real part as well as the imaginary part can be positive or negative. And then you have to sum over all the paths. And then of course, when you get the wave function, you have to ensure that the wave function is normalized, and therefore you have to multiply this by a suitable factor, which I have written n as n. This is a fairly complex thing. I don't think we will get time to discuss the details of this, but this is the idea. You can write the wave function as a sum over all the possible paths. And what is action? This is only a reminder. We physicists definitely know what is meant by action. If the electron followed a particular path at each instant, it will have a position. You know the position as a function of time. So if you know the position as a function of time, you can calculate velocity. And from velocity, you can calculate the kinetic energy at each instant of time. And imagine there is a potential. The electron is moving in presence of a potential. Therefore, at each instant, you know how much its potential energy is. So therefore, you calculate the difference between kinetic and potential energies and then integrate from the initial time to the final time. You get what a classical mechanics person will refer to as the action. Now, interestingly, in quantum mechanics, exactly the same thing occurs. And how does it occur? It occurs here. Sorry that I missed it. It occurs here. That classical mechanical quantity, which you refer to as the action, is the one that determines the contribution of that path to your wave function. So if you wanted a more precise expression for a particle moving in one dimensions, of course, action would be half mv square. X dot is the velocity of the particle, so x dot square will be the velocity square. So therefore, this will be the kinetic energy, and that will be the potential energy. For a given path, you integrate it from 0 to t, you will get the action. Now, the one of the very nicest things about the path integral approach is that classical mechanics actually follows. If I did some little bit of hand waving, I should tell you that this is not very rigorous, but it is very interesting to see classical mechanics follow from quantum mechanics if you use this path integral approach. So in fact, what as I usually say, classical mechanics is only a hand wave away. So imagine you have a particle, right? These are different possible paths that the particle could take starting here. Well, I should tell you, I should mark the horizontal and the vertical axis. The horizontal axis is time. Okay, the horizontal axis, I wish I had written it. I don't have any way of writing it now. So horizontal axis is time and the vertical axis is position. And so therefore, this is a one-dimensional problem where I plot the position of the particle as a function of time. And what is happening is that the particle is initially here, and I want to calculate the wave function for the particle at the final location, which is actually at this location at the time t. So therefore, when I say location, actually that is specified by the value of x corresponding to that. So therefore, I have to think of all these paths which join the initial position and time to the final position and time. So therefore, these are three different or four different possible paths that I have to think of. Each path will make a contribution to the wave function, and therefore, what I will do is I will calculate the action for this path, then take its exponential e to the power of is by h cross. I will do the same thing for this blue path. I will do the same thing for this path. And I will do the same thing for the green path. So these actions for the different paths are different from one another. Okay. So if you now think of an arbitrary path like this green path, and if you think of the action that corresponds to the magenta path or the rose colored path, these actions will be different. The value of S for this and the value of S is going to be different. And that difference is something that I will denote as H cross. Sorry, as delta S. And imagine that you are thinking of the limit where H cross is very small. You see, you know that in order to get classical mechanics, you have to assume that H cross actually goes to 0. It is very small in comparison with the other quantities in your description, right? The value of action for your particle is much, much larger than the value of H cross. So if the delta S for this and the delta S difference between these two paths is very large, then what will happen is that this delta S is much larger than H cross. Now this is a point where I need to write something down. Let me see whether I can manage to do that. Once again, this is my position along the vertical axis, that is time along the horizontal axis. And what I am saying is that you see, you think of this path, it has an action S. You think of another path which is like that, it has an action which is different. So therefore you have e to the power, sorry, S plus delta S as the action for that path. And then when you calculate the contribution from these two paths, what is going to happen is that you will have e to the power of I S by H cross as the contribution from this path, plus you will have e to the power of I plus I S plus delta S divided by H cross. Okay, and in fact, if you like, you can say, okay, This is approximately e to the power of is by h cross into 1 plus e to the power of I delta s by h cross. Now, when you think of that, you see, I told you, if you are thinking of the limit where h cross is very small, if h cross is very small, what will happen is that you see this object will be very large, and e to the power of I into a very large number, what is the likelihood? You see, you will expect that, you see, in all likelihood, what is going to happen is that it is, on an average, it is going to cancel this one. So therefore, when you think of summing up all the contributions from neighboring paths, what will happen is that in general, in the limit where h cross tends to 0, all these paths will interfere destructively with each other, and therefore the net contribution will be how much? It will be 0. On the other hand, suppose I say that, okay, this is, one second, let me draw that again. Let me say that this is my, okay, I mean, I didn't want it to be a straight line, so let me correct it. This is my, let us say, my classical path. And now let me think of a path which is neighboring to it, something like that. Or another one which I'll draw with a different color. So this is my, the blue one, the initial one is my classical path. Let me mark the classical path. This is my classical path. And I know the action for that. So let me say that that is as classical. But then what is the property of the classical path? You see, classical path has the property that if you varied the path a little bit about it, the action doesn't change. So therefore, if you think of such small deviations from the classical path, you see, even for this path, the action will still have the same value. It will be as classical. Even for that red path, the action will still have the same value. Why? Because for the classical path, delta S, for small variations around path, delta S is 0. So therefore, if you think of adding up contributions from all these paths, right, all of them will make the same contribution, e to the power of I as classical divided by h cross. So therefore, you see, in the limit where h cross tends to 0, what will happen is that, you see, if you think of a path like this and another path in the neighborhood, these paths will actually tend to cancel each other when you calculate the path integral. But the paths around the classical path will actually, the contributions will not cancel each other, and therefore they will add up. And therefore, you see, it is fairly easy to realize that in the limit h cross tending to 0, only the classical path and very few paths near it contribute, and therefore path or a small set of paths around it are the ones that are important, and therefore you realize that classical mechanics follows as a hand-waving argument. So that is what is being done here. If you think of a path like this, the blue path, and it is not a classical path, then what will happen is that the contributions of paths from the neighborhood, they will cancel each other. Whereas if you think of a classical path, this is the classical path, let us say this is the classical path, and if you think of paths around it, these paths also make the same kind of contribution, and therefore these contributions add up. So therefore you realize that, you see, from my ideas of path integrals, I get classical mechanics very easily. Why do I get the ideas of classical mechanics? The idea is that in the limit where h cross tends to 0, only paths for which the principle of least action is obeyed are the ones that are important. So therefore the idea of principle of least action in classical mechanics follows straight away from the path integral approach. So let me kind of summarize what I have been doing. So the idea, what is the idea of this whole thing that I'm talking about? See, the whole idea is actually you have integration over a space of functions, which is different from your usual ideas of integration. So in the usual integral that you encounter, let us say I have integral, something like a to b, integral of a to b, f of x dx. You are actually integrating the function f of x, which is plotted here. This is the function. And when you integrate from a to b, f of x dx, what are you actually doing? You are actually integrating over a set of points. What are these points? These points actually extend over the interval from a to b, which is shown here. That is the interval that you are integrating over. And if you wanted a more precise definition of the integral, what you do is you sample your function that is being integrated at different points along the interval. You consider dividing that interval into smaller intervals, and then you sample your function. Right? You divide this into intervals of length delta x. So at each interval, you sample the function, take the sum, and then multiply it by delta x and sum. And then you allow the limit where the number of intervals goes to infinity with the condition that n times delta x goes to the length of the interval, and you get the value of the integral. So integral, normal integral, or the integrals that you are familiar, has contributions from all the points that lie in the interval a to b. And therefore, I can say that you are summing over a set of points in the interval. Of course, the number of points in the interval is infinitely large, but that doesn't matter. This is the idea. So you are summing over a set of points. Of course, the set has infinite number of points, but that is only a mathematical thing. Now, on the other hand, when you think of functional integrals, what is it that you are doing? First of all, you are thinking of function of a function. As a typical example, what I'll do is I will think of this kind of object. You see, for example, I am thinking of x of s. X of s is a function. Why do I say that it is a function? For each value of s, there is a value that is assigned to x. So therefore, it is a function. And if you know this function, x as a function of s, what you can do is you can calculate x dot square, essentially kinetic energy here. And you can also calculate the potential energy and then take the difference and then integrate from 0 to t. Okay. And then after having done that, what I will do is, okay, I have been a little bit careless because you see, this is the kind of thing that occurs in tunneling problems. I will not go into the details of that, but I should have had not a negative sign here, but a positive sign there. But it doesn't matter. I mean, I made a mistake in typing my formula. The good thing that I realized the error, this is going to be a positive sign. So this essentially, the only thing that I want to say is this is a functional of the path that I think of. Then I multiply it by 1 by h cross and take its exponential. This is a nice object. And in fact, the thing that I want to say is that you give me any x of s, I can give you a number, right? So you give me any function, I can give you a number, and that is what I refer to as a functional. And once I calculate the functional, what I do is I take this sum over all possible functions. So therefore, I integrate over all possible functions such that all the functions satisfy this condition at the time 0. They all start at the origin. And at the time capital T, they all end up at this point xf. And that is actually the process of functional integration. So you are essentially summing over all the sets of functions. And that is where things are more complex and interesting. Okay, this idea, as I originally introduced by Wiener in the theory of Brownian motion, this is Norbert Wiener, a mathematical genius. In fact, if you find the subject interesting, what you should do is you should read this nice book, Nonlinear Problems in Random Theory, published by MIT Press. This was published long ago, probably around 1929 or so, but you can find copies. I mean, if you know where to find, you can find e-copies of the book, and this is a very nice book to read. It actually introduces the idea of functional integrals. He doesn't use the word functional integral as far as I can remember, or maybe he does. Anyway, the ideas of Brownian motion. The theory of Brownian motion is introduced and rigorously analyzed in that book. And this was done in the ideas. Wiener had this idea in 1918. And then, as I have told you, the same kind of idea was introduced into quantum mechanics by Feynman in his PhD thesis around the year 1942, if I remember correctly. This is Richard Feynman, another genius. And he has outlined his approach to quantum mechanics in what is known as, in a book known as Quantum Mechanics and Path Integrals. Very nicely written book, but of course, unless you are very interested or you have a talent for mathematical equations, this book is not so easy to read, but if you can read it, it is an absolutely fascinating book. And so he is the one who introduced the same idea, the idea of Norbert Wiener. The same idea was completely independently introduced into quantum physics by Feynman. And as I have already told you, the ideas of Wiener, he put them on a very firm mathematical basis, whereas the idea of path integrals, you see, the mathematical basis for path integrals actually, as far as I know, I mean, when I was a student, I used to be very much interested in the mathematical formulation of path integrals that were introduced by Feynman, but I am not, because my expertise in mathematics is not enough to work on this kind of problem, mathematical basis for the Feynman path integral. At least 20 years ago, this was an unsolved problem. There have been people working on it. Maybe it is completely solved now, I have no idea. So if the students find it interesting, they can look up the papers on this and see whether it is completely understood. But I have a doubt that it is not completely understood. So how does one evaluate the path integral? Well, this is only one slide. I will just flash because I have run out of time. So you see, the idea is I want to evaluate the path integral. Imagine I want to do the path integral for a particle which is starting at xi at the time ti. That is what is marked here. I say that the particle starts here at the time xi, at the time ti, and I want to calculate the path integral for it to be found, or the wave function for it to be found at the position xn at the time tn. That is my final time and final position. So how do I do that? How do I evaluate the sum over all these paths which start here and end there? One possible way in which you can think about it is, you imagine, you think of straight line paths starting here and ending there at the time, starting at this location and ending at x1 at the time t1. Then another straight line path starting from there and ending there at the time t2, that is at the position x2, then going to x3 at the time t3, and so on, eventually ending up at xn at the time tn. So therefore, instead of considering a curved path, what I am imagining is that I have a straight line segments. So from here to there, it follows simply this straight line. From there to there, it follows another straight line path. From there to there, it follows another straight line path, and so on. And if you thought of such a straight line path, you can actually write an approximate expression for the action. So that is the crux of it. So for example, if you think of kinetic energy, you see what will happen is that the integral kinetic energy is actually, the kinetic energy contribution to the action is actually this integral. You take half mv square, integrate it from the initial time to final time, and that is the integral of kinetic energy from initial time to final time. And if you think about it, you see how is the kinetic energy? Well, if you say that the particle starts here at x, let us say at x1 at the time t1 and ends there at the time at position x2 at the time t2. In order to calculate the kinetic energy, what you have to do is you have to subtract x1 from x2 divided by the time interval t2 minus t1, correct, which I will say is delta t. T2 minus t1 I will say is delta t. So therefore I will take x2 minus x1 divided by delta t. That will give me the velocity. I will take the square of that. that will give you the velocity square. You will multiply it by m and divide it by 2, and I have to do it for each such interval, sum over all such quantities. So therefore, initial final position divided by initial position, final position from which you subtract the initial position divided by the time interval, take the square, you will get velocity square multiplied by m by 2, you will get kinetic energy multiplied by the time interval that is available, and then sum over all the possible intervals, you will get the integral of kinetic energy. This, of course, is an approximation. Then similarly, you can write an expression for the integral of potential energy from the initial time to the final time. It can be approximated by this discrete sum, and if you agree with that, then the action would be approximated by this expression. And then, of course, you may say that this is an approximation, and once you take that approximation, what is it that you have to do? You have to take that approximation into the exponent. So therefore, in here, instead of this s, you have to put that expression. And how do you sum over all possible paths? That is where things get interesting. You have to assume that this x1 can be anywhere between minus infinity and plus infinity, because the particle could take any possible path. So therefore, you say that x1 varies between minus infinity and plus infinity. So you integrate over all possible values of x1. Similarly, you have to integrate over all possible values of x2, then all possible values of x3, all possible values of xn minus 1, and therefore you have an infinite number of integrals. And then, of course, you have to sum over all the possible paths. How will I do that? Well, I will have to assume that the number of slices of the time interval that I have taken, they will go to infinity. So n goes to infinity. At the same time, I will assume that the time interval itself goes to 0. So therefore, you have infinite number of integrals here. And this has to be multiplied by a suitable normalization factor, which works out to be this number. And I have made another small mistake here. This n that is written there should have been inside. It should have, this should have occurred after this. This should have occurred. This expression should, this n should have occurred here, and only after that I should take the limit delta t tending to 0 and going to infinity. And when I wrote this slide, the equation, I did not notice it. So this is the way it is to be done. And once you do that, you see that is the kind of object that you would write as a functional integral. And as I have told you, if you have this kind of functional integral, that is actually equivalent to solving the partial differential equation, the diffusion equation. And well, I have to overshot by 15 or so minutes. So I hope that it is not harmful if I overshoot by another 2-3 minutes. So this is a slide that I usually slow because it has relevance to Cochin. Let me show this. You see, if you went to Cochin city, Ernakulam town actually, then in the 1980s, you see what happened was when I was living in Cochin, you see that that time the corporation actually decided to dug up the roads. I mean, so therefore the whole place was full of big holes. And with this rainy season, these holes will get filled with water. So therefore, imagine the drunken person walking in Cochin city in those days. And what will happen is that you see there are big traps for the walker. So therefore, if he walks, you see, he can eventually end up being trapped in the wall. He may die. So this is actually, he may fall into the trap and remain there until, let us say he doesn't die, but he falls into the trap and he cannot escape. And so he falls in the trap and remains there until the following morning when somebody finds him. So this is actually something that you will refer to as a random walk with absorption. So if you think of such a walker, so you see this kind of functional integral, as I told you earlier, is something that will arise if there is no absorption, but then it is possible for you to introduce absorption also into the problem and modify the path integral. How does it get modified? Well, it will get modified by a particular term, which I write as this. So therefore, you introduce an absorption term, which itself is a functional of this path. So A is the absorbing term, and this will determine the probability that this object will determine the probability that the person will survive if he followed that particular path. And therefore, this is the simple modification of the functional integral to take care of absorption. Again, if you think of not doing path integration or functional integration, then what you do is you will solve the differential equation, and what is the corresponding differential equation? The differential equation in this case also is simple. What happens is that you have a modification of the diffusion equation. This, if you had this term only, then it is actually a diffusion equation. But now you say that there is absorption, so therefore this is an diffusion absorption equation, or as chemists will say, this is a diffusion reaction equation, and this is the equation that you have to solve. So therefore, if you had a diffusion or a partial differential equation which is of this form, interestingly, there is a path integral representation for that, which is having that form. And therefore, if you do not want to solve this partial differential equation, what you can do is you can think of solving this path integral. And in fact, this is another one of my favorite subjects, because usually many times I have been interested in diffusion with absorption, and instead of considering solving the diffusion equation, I usually many times think of solving the corresponding path integral, and it leads to interesting insights. Okay, let me not worry about that. Now I have come to the end of my talk. I'm sorry that I have taken a little bit more time. I have tried to keep the mathematics a minimum. The idea is that, you see, the students should find it interesting. Hopefully they would have done so, and they would be motivated enough to pursue the topic further. And let me repeat what I said in the beginning. In my opinion, the ideas of path integration makes the ideas of path integration makes quantum physics as simple as it can be made. And in my opinion, quantum physics cannot be made simpler than this path integral approach. The idea is just beautiful. Evaluating a path integral is a messy subject, and many a times I joke. See, path integrals are very nice to think of, but if you wanted to evaluate, it is actually easier to solve the Schrodinger equation rather than evaluate the path integral. But having said that, you see, there are ways in which you can write path integrals that there is no corresponding Schrodinger-like equation. There are situations where there is no Schrodinger-like equation, and therefore you have no way, no choice other than to evaluate the path integral itself somehow. I have not discussed such interesting problems in my talk, but there are papers of mine which discuss such cases. And even now I am writing a paper which discusses such a situation. But that is only to motivate the people who are interested in research to study the subject further and perhaps take up the study so that you will be able to use in your research. Thank you very much. And I would like to thank the organizers, and of course, those of you who have survived the talk, I would like to thank them all for listening to me. Thank you.
Diffusion equation is a path integral.
Well,
diffusion coefficient du measure same notation.
1 second. What was the comment actually? This is not a question, it is a comment. What was the comment?
Now you have a path integral dx, right?
Okay. Yeah, well, I see the point. Well, you see, this is standard notation, unfortunately.
You can put script d or something like that. Yeah.
Yes, I could. Thank you. In future, I'll be more careful. I don't know whether the students have understood the question, but this is essentially about notation. Let me see whether I can get this slide back. Yeah, what he is saying is that, you see, you have a D here and another D there. I hope you can see my screen, right?
Yes.
What he is suggesting is that this D, I should not have used the same symbol. I agree fully. Well, you see, the problem is one is very familiar with this topic. One doesn't notice such things. I should have used a script D here. That would have been the best thing, because this D is diffusion coefficient, and that D actually is just a symbolic notation standing for summing over all possible paths. Yes, that is correct.
And in the final expression in somewhere,
Yes.
you mentioned it is tunneling coefficient. So that may be the reason you missed I also, I believe.
Yeah.
Is
Well, you
it?
see, in that case, I was thinking in imaginary time quantum mechanics. I didn't actually go into the details of that.
But that expression was, there was no I, right? Suddenly it was
Yeah,
just,
because essentially I'm doing statistical mechanics. Okay, that's why I
yeah.
said this is a plus sign.
Yeah. And there is no I by H.
No, there is no I by H. If I am doing statistical quantum, this is actually, I mean, this is a kind of thing actually occurs in quantum statistical physics.
Euclidean formulation.
Yes, so therefore that's why there is no I, and in fact, in Euclidean formulation there is a positive sign. Well, you see, I just wanted to demonstrate a functional. So this is a functional, perfectly acceptable functional. What you are saying is that if it is to have physical relevance, you see, you should have probably a beta H and so on. Let us not worry, get into too much detail because I don't want to frighten the students, but this is only an example for a functional. Interestingly, such functionals can be used in quantum statistical physics.
It is.
And this
But a
kind of thing,
partition function is a functional of,
yes, this is actually an expression for the partition function for one particle. Quantum mechanical partition function for a single particle moving in a potential V of x. But for that to be true, actually, there should be a plus sign here. And T should be related to the temperature. The T that is occurring here, actually, it would be referred to as beta H cross, where beta is 1 by kBT. I think I am going too fast. The students are unlikely to follow, but for the sake of correctness, let me just say that. If you are doing quantum statistical mechanics of a single particle, then you will have a positive sign here. This T will be actually equal to beta H cross. Beta is again standard notation. And this beta will be equal to 1 by kBT, where kB is Boltzmann constant and capital T is the temperature.
Yeah,
Okay.
so now my question is about this normalization constant. So what is it normalized over? Is it over the...
No, that is a messy thing. See, I have put everything under the rug.
Okay.
If you know the phrase.
Okay.
A little bit of cheating. Where was that formula? Yeah, well, you see, if you look at this, the normalization factor, this is actually for a system m divided by 2 pi I h cross delta t to the power of n by 2. That is the normalization factor. And essentially what it does is, you see, if we do not have this factor, then this integral will not be well defined, for one thing. And the second thing is it ensures that your wave function is normalized at all times. So it is in that sense that it is a normalization factor.
actually it is a normalization for Gaussian, right? Gaussian function.
It is,
Yeah.
yes, that is correct. It is a normalization factor that
Because
comes
these
from
are
this.
quadratic.
Yes.
Your potential, kinetic energy.
Yes. Actually, this expression is 1 second. It is valid in general. Actually, the potential can be anything.
But if you want to do, okay, otherwise it may be difficult to calculate, but it comes from that quadratic.
It is essentially coming from this term doesn't make any contribution. It's essentially from this term that the normalization comes. Essentially ensures, you see, when you take this and put it into the exponent, you get a set of Gaussians, right?
Yes.
If suppose you had v equal to 0, then you get a set of Gaussians, and if you say that, okay, I want each of my Gaussians to be normalized, then this is the normalization factor for each Gaussian, and because I have n Gaussians in the sum, I will have m divided by 2 pi I h cross delta t to the power of n by 2.
Yeah, so I mean, yeah, my doubt was about why it is needed physically, because I can't see why each Gaussian has to be normalized. What is it? Is there a reason?
Your ultimate wave function itself has to be normalized. If you did not put it, your wave function will actually be infinite. It will be 1 second. What will it be? It will be 0.
It has to be finite at least. Normalization may not be
No,
possible.
it won't be even finite. It will go to 0.
Yeah, but we have fixed the initial and final position and time, right? So that's
No. But you see, you look at delta t. Delta t is sitting in the numerator. So as delta t tends to 0, this term actually blows up. It goes to infinity.
And sir, when you when you take expression values, this term gets cancelled, right?
Yeah. This time, I mean, when you calculate, even for a free particle, if you look at it, you see this is being evaluated in the book by Feynman. The integral actually is done explicitly in the book by Feynman. And you will see that the answer is actually very, very well behaved, and it describes the propagation of a free particle. With this term, if you did not put this term, you say you will not get an answer which is finite. You will get the answer to be 0.
In fact, this is the propagator from
It is exactly the propagator.
Yeah. So if you want a propagator to be finite, I think you have to put this thing. Otherwise, there will be a problem.
For those of you, I mean, who are fascinated by the subject, actually, this expression, once you assume the Schrodinger equation, you can derive this. I mean, if you are not familiar, I mean, for somebody who knows, this is trivial. But let me just say this: you take the Schrodinger equation, write the solution as e to the power of minus I Hamiltonian divided by h cross into t. And then from that expression, actually, you write the time evolution operator. From the time evolution operator, it is a fairly simple matter to derive this. If you want a reference, you please refer to the book by Schulman. What is it? It is called Techniques and Applications of Path Integration. Schulman, very, very nice book, but more advanced than the book by Feynman. One of the books that I love, actually, Techniques and Applications of Path Integration.